Thank you. Well, I'm pleased to see at least some of the faces by Zoom, and I'm really sorry that it couldn't come. I visited Toshi in 2014 for 2 weeks at the same place, University of Tokyo, and he was such a wonderful host. I mean, certainly, that was one of the nicest visits ever. And, best wishes to Toshi and for his birthday. Well, I guess I should start with my lecture now. So I'm going to talk about exceptional theta correspondences. In fact, for real groups, I don't write too many papers on real groups, but I recently wrote one with Locke. It has been a couple of years already, but since I also do not attend so often conferences on real league groups, I didn't really have opportunity to give a talk on this. And also this fits nicely with the common interest I have with Toshi. These are minimal representations. So I think this is kind of appropriate for this venue. So my talk will consist of basically 4 parts. I'm going to try to explain dual pairs in exceptional groups or Lie algebras. Then I'm going to quite generally explain what a theta correspondence would be. And then I'm going to a little bit explain about minimal representation that we're going to use to get the theta correspondence. And you will see that for particular dual pairs, I'm going to discuss minimal representation is pretty much the only that possibly can give some nice correspondences. And then I'm going to talk a little bit about the proofs. In fact, those proofs will kind of justify what I just said. So let's go and start with proofs. Sorry, with dual pairs, not the proofs. So, classically, how dual pairs, you take symplectic and orthogonal space, you tensor them, you get larger symplectic space, and then you get naturally symplectic orthogonal dual pair and so on. One natural way to look at dual pairs in exceptional groups is through Tits constructions. So let me explain what this thing is. There are so many Tits constructions, so when you write something like Tits construction, it's pretty much meaningless. So I'm going to start, and again, everything will be over real numbers. So Lie algebras will be over the field of real numbers. So I'm going to start with octonian algebra O. Over real numbers, there are 2 up to isomorphism, isotropic and non-isotropic. And then G2 can be defined as automorphism group of octonian algebra. That's a nice definition. And then we need another thing, a Jordan algebra, so-called Freudenthal Jordan algebra. And you see, of course, I'm sure, this audience is familiar with Jordan algebras, and Freudenthal Jordan algebras are cubic Jordan algebra. So in particular, you can write it as 3 by 3 Hermitian symmetric matrices over a composition algebra. So Q is a composition algebra, and over real numbers, composition algebra can be real number, complex numbers. This is a non-split form. Quaternion algebra, split form of quaternions is matrices, and then octonions. And what is really important for the Jordan Freudenthal algebras is the norm form, which in this case is a cubic form. And once you pick a non-degenerate element, this pretty much uniquely determines the structure of a Jordan algebra. So instead of Jordan algebras, one can talk about pointed cubic space. So that's in some sense important. I will just point out that one can easily now compute dimension in each of these 4 cases. And here is how Tits has constructed exceptional Lie algebras. H, you take the algebra of derivatives of O, then you add to this the algebra of derivatives, the Lie algebra of derivatives of J, and then plus 3 zero octonions, tensor 3 zero elements in Jordan algebras. So these are natural modules for, well, O0 is 7-dimensional representation of G2 and its Lie algebra, and J0 is natural representation of the Lie algebra of derivatives. Or if you wish, when you pass on groups, you will have G2, which is automorphism algebra of O times automorphism algebra of J. That will be a dual pair in automorphism algebra of automorphism group of H. So the group of automorphisms of H is essentially, Lie, I mean, simple Lie group corresponding to H. However, it can be disconnected in E6 case. And just as in classical theta correspondences, you really need to work with disconnected groups, it's actually more natural, to take the group of automorphisms of an object rather than connected component of it. Okay, so this is the Tits construction I mentioned at the beginning. Of course, the difficulty is to write down the bracket and verify that this indeed actually gives you, Lie algebra of type F4. Let me write it here: F4, E6, E7, and E8 as you run through these 4 composition algebras. And this is very difficult. So let me actually give you another quick course how we actually can see these dual pairs in these Lie algebras using Dynkin diagrams. So I'm going to quickly try to write down the so-called extended Dynkin diagrams for F4. And here is for E8. I hope I'm going to get it done quickly. 1, 2, 3, 4, 5, 6, 7, I guess 8. Then E6, that's one is easy. Extended. And finally E7. And now if you group together these pairs of simple roots, well, they will span the copy of SL3 in each of these cases. And then, of course, you can cross out this neighboring root. Of course, you see, when you add a negative highest root, I mean, you get dependent set of simple roots, but when you remove one, then you get back independent set of simple roots, but it spans a smaller sub-algebra. I'm going to call this L, and you can see what this L is in each of these cases. And let me make a small table of these things right here. So we have H, which can be F4, E6, E7, and E8. Then we have, in fact, I'm not going to call this L, I made a mistake. I want to call this M. So M is a sub-algebra, and you can see I'm going to write the type. So I'm going to write this A type, A2 tilde in this case, because this is M in F4 case, but these are now short roots, so that's why we have tilde. In this case, we have A5. Here we have A5, and what do we have? No, that's wrong. A5 we have here, because I forgot to cross out this root here. Apologies. Across this. So M consists of these two pieces. So it's A2 squared. Well, and in this case, we have E6, this kind of most exciting. E8 is an amazing group in the algebra. Okay, and then now each of those M's has evolution of order 2. You know, E6 as you know, and a fixed points is F4. In this case, evolution gives C3. In this case, I'm flipping these two pieces. I get A2. And here I have like transpose inverse. So I'm going to write this as SO3. That's what we really have. I mean, some sort of SO3. Okay, that's the G inside M. And of course, this is all very elementary for all of you guys. So inside H, we have SL3 plus M. And then you see, you know, SL3 has a center, mu3. So that mu3 will actually give, you know, mu3 grading of Lie algebra, where the trivial, identity piece is SL3 plus M. And then you're going to have, under the adjoint action of SL3 on M, you're going to get the following. You're going to get V tensor J plus V dual tensor J dual, where of course V is an SL3 module, and you can see what this module is, because you see these two summands will be, you know, you will get them from this root that you removed, right? And you see this root will give you fundamental weight for SL3. So see, dimension of V is just 3. It's three-dimensional representation of SL3, and of course you get the contra gradient, so dual piece here, and you can see actually, let's go up here. If you look in E8 case, you see this root that you removed will give you fundamental weight for E6, which corresponds to 27-dimensional representation. So I can actually just write this down, what the dimension of J is, and you know, you can see, for example, in this case, you know, dimension is 27-dimensional. In this case, it's 15-dimensional, and here it's 9-dimensional, here it's 6-dimensional. And so this is exactly the dimension of that Freudenthal-Jordan algebra. In fact, you can, using Lie brackets, you can put a structure of Jordan algebra on this. In fact, you can first, using Lie bracket, define the cubic form on J. And then, you know, how do you know, to specify Jordan algebra structure, you just have to choose a non-degenerate element in J, and that will be given by a vector fixed by G. You see, like, if you look at this exceptional case, you have 27-dimensional representation of E6, and F4 is just the stabilizer of a line. So, in other words, if I take the centralizer of G, inside H, so again, G sits here, right? Well, then what you're going to get SL3 plus, you're going to pick a line in J and a line in J dual, so you get SL3 V plus V dual. Well, and now you're having, you know, basically, you know, semi-simple Lie algebra, you know, which has Z-mod3 grading with SL3 as a 0 piece of the grading, and then you have 2 3-dimensional representation here. Well, of course, you recognize this as a G2. So you get, you know, from this you see that G2, you know, times, you know, G, it sits inside H, and it's a dual pair. And then when you pass on, so these are the dual pairs I'm going to be looking at. And so if you pass two groups, you get the following. You get that, G2 times automorphisms of J sit inside the automorphism of H. And this is now totally evident, in split case. I'm just using Chevalier construction of these algebras. And then the same is true when you do Galois cohomology. I mean, you have this map that is. Okay. Of course, it's automorphisms of H, so H1. Oops, H1. H1. I forgot R, but it's okay. So what this thing parameterizes forms of rational forms of H. Well, what this parameterizes rational forms of J. And this parameterizes forms of octonian algebra, because G2 is automorphism group of octonian algebra. So this is just a kind of formal nonsense of Galois cohomology. And so basically, this tells you, given the form of octonian algebra, form of J, you're going to get form of H. And of course, this is just a Tits construction. So in some sense, Tits construction is some sort of functoriality in Galois cohomology. And you can view many of the classical constructions like Koeher-Tits construction in this way. Again, so Koeher-Tits construction can be also viewed in this way. So in other words, just as functoriality of Galois cohomology. And this is a view that actually we have taken in joint work with Kobayashi. I have one paper with Toshi. And there we discuss this for this Koeher-Tits construction. Okay, so this is all I wanted to say about dual pairs. So next thing are theta correspondences. Maybe I go to next page. Okay, so again, I start with some representation pi, and I'm going to go to the language GK modules. So this is an irreducible H L module. So L is the maximal compact in H. And then here we have a dual pairs. I'm just going to discuss this abstractly. So we have a dual pair inside H, and we also have a K and K prime as maximal, sort of say maximal compacts. For G and G prime. So again, in our case, eventually G is going to be G2 and G prime is automorphism group of Jordan Freudenthal algebra. But here I can just do this very abstractly right now. And so if you start with an irreducible GK module, so let V be an irreducible.
Excuse me, sorry, I have a question. G and G prime are in H or L? I'm confused.
G and G prime are in H, yeah. Okay. So again, for example, H is E6. And L is just the maximal compact, the V6,
okay,
right?
okay, I believe the opposite. I was thinking that H is maximal compact. Sorry, it's L.
Yeah, no problem. So age is, sorry, for example, if age is, no problem, just ask questions. So age will be one of the exceptional. So just going back a couple of pages, you see, remember, you see we have this G2 times G in H. So G prime is, let's say, G2, and G is this automorphism of J, or derivatives rather in this case. So, I mean, the nice dual pair is really G, Z8, and then inside, you know, have G2 times F4. I mean, this is like the most exceptional dual pair. Other dual pairs are just, you know, I didn't really emphasize. You see, so the dual pair is G times G in H. So one is G2. That's, you know, when you pass the groups, you get G2. And so these guys are here. SO3, A2, it's really disconnected. It's PGL2, semi-direct product Z mod 2, and here is PGSP6 and F4. So these are really these dual pairs. Yeah. And so I start with a reducible GK module, and then you can take pi modulo intersection of all kernels of all homomorphisms phi from pi to v, of course, intertwining, I mean G intertwining. And the fact is that this can be written as some theta of v, tensor v, so you need this to be reducible. So where theta of v, this is also called big theta lift, is a G prime K prime module. Okay, so this theta v is what you would call a theta lift. So this can be done completely general. You know, all you really need the G and G prime commute with each other, and pi can be any. Doesn't even have to be reducible for that matter. HL module. And so this theta v is what's called big theta lift. But here's what you want. And so here is the desiderata. So you want the theta v has finite length. And it's cyclic. That means has unique irreducible quotient. And similar when you start with, you know, irreducible GK module V prime of G prime K prime. So, you know, I'm squeezed with space here. I'm not going to write it. So going both ways, you can define this big theta V, and you want it to be finite length and to has unique irreducible quotient. In that case, you know, this unique irreducible quotient is also called the small theta lift, and you know, this, if you have both ways these statements, then you have one-to-one correspondence, and these two things can be called, how should we call it? This is some sort of Howe duality, right? So Howe duality. Okay. So next thing I want to explain a strategy of proving Howe duality. Howe duality, and of course the strategy is due to Roger Howe. Okay, so I'm gonna do this for split groups for excuse me, and spherical representations. So all representations, spherical, in particular pi. Remember, pi is the representation of the large group, right? And we want to restrict it and to do this duality, theta correspondence business. So first thing, I'm going to, of course, assume that that L fixed vectors in pi, this is age L module, it's one-dimensional, spanned by V0. V0, of course, non-zero spherical vector. And then I would like to prove the Howe duality conjecture for spherical representations of G and G prime. So in terms of GK modules, so I would like to prove this Howe duality. So how do you prove this? So here's what you need. You need to do the following two identities. You take, remember, you have this dual pair G times G prime inside the H. In particular, you have this K times K prime. These are maximal compacts inside L. Of course, V0 is an element in pi K times K prime. I mean, a fortiori. So sort of say, kind of joint type for both K and K prime. And so what you really need to prove the following two identities. So when you act on V0, which is also fixed by capital K, and when you act by G prime, of course, G prime commutes with K, so it's clearly, I mean, this is contained, UG prime V is contained in pi K prime, but what you want equality. And also vice versa. You want K prime fixed vectors, you want to. Okay. So of course, Roger Howe's this wonderful strategy of proving this Howe duality in general for classical theta pairs, and then the same game is played with so-called joint harmonics. Unfortunately, in exceptional theta, I don't know how to define joint harmonics because structurally something fails there. But for spherical representation, this spherical vector for this large, later we'll see minimal representation will play the role of this joint harmonics. And so once you do these two identities, then you're done. So I'm not going to actually go explaining. It's really not that difficult to see that these two identities prove the Howe duality, for theta correspondence. So instead, I would like to explain how to execute this strategy. For minimal representations of exceptional groups of En. You see, eventually I'm going to drop F4 because minimal representation of F4 lives on a two-fold cover. I mean, there you can also do theta correspondence and so on, but you're not going to have spherical vector exactly. So and therefore I'm going to move to Ens only in a moment. And what else I wanted to say? Yes, I would like to say just as observation that we have a Cartan decomposition. I'm not so sure if this is the right moment to write this, but maybe it is. And because this vector V0 is fixed by K, and you see the bracket of two elements in P ends up in P, this really is just sort of say S of P acting, so this is just symmetric algebra on P acting on V0. Again, this is not important observation, at least, we're gonna realize that, this thing, it's just a polynomial algebra, so it has some sum of homogeneous terms and so on. Okay. It just helps you realize that there is some sort of natural grading on this space, if you wish. Okay, so I would like to explain this, how we're going to actually prove this for minimal representations of group Cn. So we need to go to the next part of my lecture, minimal representations. So for real groups, this, as far as now, started with David Vaughan. Of course, oscillator representation is also minimal representation, although, I mean, it's sort of slightly, it's, you know, it is, although in many ways there are some sort of different phenomena. And of course, so many people work on it, certainly, you know, Toshi's work. And together with his many collaborators, it's here very important, if not most important. And so for us, I can define minimal representation simply, you know, because I'm dealing with split groups. So this is a simple definition: spherical representation annihilated by the Joseph ideal. So I don't have time to go in Joseph ideal, but, you know, Joseph ideal determines infinitesimal character, and because the representation is spherical, we're dealing with split groups and so on. This basically uniquely determines for, you know, split groups of types E. And so L types of pi, I mean, minimal representation, I should really write minimal, but maybe a spherical representation pi annihilated by. Of course, you have to prove that such thing exists, but L types of pi, they form a string or a ladder. And of course, here tau 0 is just a spherical type, so this is a L fixed line. And in this in our situation, G is not of not G. H is not of Hermitian type. So if you write a Cartan decomposition, so this is Cartan decomposition. So of course, P is just generated by the enveloping algebra of H acting on tau 0, spherical you know, line. But of course, L kills tau 0. So what really does, you know, this S will just sort of say shift tau 0 in tau 1. And of course, tau 1 is nothing else but S as L type. As L type. Again, we are not in Hermitian symmetric space, so S is in irreducible L module. And so that's why, I mean, this minimal representation is unique more or less. Once you go in, once you take real groups which are Hermitian symmetric type, then minimal representation typically going to have homomorphic and then anti-homomorphic, and symplectic groups have another level of difficulty. You're going to have 4 actual representation. Okay, so you can see from this that these are really this, you know, the minimal collection of types that any infinite dimensional spherical representation can contain, because again, just by acting by the S, I mean, you know, tau 1 will be pushed to tau 2 and so on. And this cannot stop, otherwise you're going to find a dimensional representation. So from the perspective of types, I mean, this minimality is really clear. And also, it's unitary. That's another important thing. And why is this important? Because there is another characterization of the minimal representation. Of pi for these groups ENs, basically, well, by a well-known theorem of Howe, matrix coefficients of unitary or unitarizable representations decay in infinity, and we're talking about irreducible unitary representations. And also by theorem of Gordan, because these groups of type En are rank at least 2, we also know that trivial representation is isolated in the unitary dual. Now, of course, you can ask a question, so what is the closest representation to trivial representation? This sounds bad as I mean, the way I said it, because unitary dual is not a metric space. But still, what you can do, you can measure how fast the matrix coefficients decay. Of course, the slowest decay or no decays for the trivial representation. And the fact is, and this is due to myself and Hangi and Locke, that this pi minimal, let's call it pi minimal, for these groups of type En have the slowest decay of matrix coefficient. Amongst unitary representations, right? So trivial doesn't decay, all other decay, but minimal representation has the slowest, and you know, this rate of decay is also some measurement in the reverse of smallness of representation. I don't really understand that part very well. Okay, very good. So now that we know what minimal representation is, now we're going to do the proofs of those identities. Remember, we want to prove these two identities. I'm going to assume that for this dual pair, G times G prime inside H, I'm going to assume that G is smaller. Okay, and then what you prove is the following lemma. Matrix coefficients of pi restricted to G are LP plus epsilon, where P, of course, depends on G. We have 3 G's in our setting. And what is really important, it's less than 2. So in other words, they're better than square integral. And so now you can use this to show that when you restrict pi to G, that you have some sort of irreducible G quotients of pi by the very old technique, integrating matrix coefficients of pi against matrix coefficients of, let's say, tempered representations of G. And that's what I'm going to do. So I'm going to introduce just a little bit more notation. So let P MAN. So all groups are split. So this is a minimal parabolic in G, so also known as a Borel group. And then of course, we have principal, spherical principal series. And, you know, I'm going to write like pi lambda. So this is some induced representation from P to G. And of course, you take trivial thing on N, trivial on M, and just some sort of, just to save notation, some e to the I lambda, where lambda is, I'm going to squeeze here, lambda is in A star. So of course, maybe complexified A star, where A is the Lie algebra of capital A. So A is Lie algebra of A. And so this parameter lambda, you know, you can think about it as a plane. That will be the SL2 case. So here is the real axis, I guess maybe A star. Here, imaginary axis. So in other words, with lambda is on imaginary axis, you get the tempered representations, which are almost L2. And now what you can do, you can integrate over G the matrix coefficient So again, I'm not using pi of G notation just to save on writing. So V0 is in pi 0, remember? So V0 is the spherical vector in pi, right, in tau 0. And here I'm going to take a spherical vector in V lambda. And I'm going to act by G on V lambda, Vg. And you know, you can pick Q such that 1 over P plus 1 over Q equals, I believe, 1. And now Q will be, I believe, I hope I'm not making a mistake, bigger than 2. I mean, the upshot is that if you, again, maybe I shouldn't have written this P and Q because I might get things wrong, because you know, let's say matrix coefficient of pi restricted to G is maybe like L to the 3/2. That means there's going to be some tubular neighborhood of imaginary axis for which this is converging. Just from a Helder inequality, which I try to actually write down here, defeating myself in the process. And also, if lambda is 0, you know, then both of these two functions are positive, and therefore this certainly is non-zero. So when I choose lambda to be 0, this integral is clearly non-zero. So therefore, you know, on an open set, and probably, I guess, on an analytic open set, this pairing will be non-zero. So that means, in some sense, if you wish, that if you use pi and you can theta lift essentially kind of generic spherical principal series of G. In fact, let me write this more precisely. In fact, what I need is the following, that home, this is a consequence of what I said, that home, in fact, just the following I need. U of G acting on V0, pi lambda, I mean G home, it's non-zero because of that pairing is non-zero for lambda in an open set. So it means essentially, basically almost all spherical representations lift. And so, of course, remember what we want to show. We want to show that UG V0, which it's really S of P, as I mentioned, V0, it's equal to pi K prime invariance. Well, this fact shows, so star implies that the map x goes to x v0, where x is any element in S of P, is injective. Because if you had any kernel to this map, then you wouldn't be able to get generic spherical series and a quotient of this space. This is a submodule of representation pi, and so you have a control of this space. On the other hand, well, you know that well, before I get to the minimal representation, so far this argument works for any pi unitary representation, because minimal representation is really, you know, has the slowest decay. All other representation have even, you know, sharper decay. So if you, instead of minimal representation, you choose another representation, that this strip will be even wider. And so if you take any unitary representation and you restrict it to this G, you know, you're gonna, any non-trivial, you're gonna be able to lift all spherical representations from the smaller group. And so you will have this injectivity. But the fact that this is subjectivity will follow from the fact now at this point, we need to use that this is minimal representation, because this is gonna be the sum of tau 0, which is an L module, k prime fixed vectors, plus tau 1 k prime fixed vectors, and so on, right? And because of this injectivity, to prove this isomorphism, all we really need to prove is the following lemma, is that dimension of degree n summoned, homogeneous degree n summoned of P, so these are homogeneous polynomials in P of degree n, is equal to this dimension of k prime invariance in tau n. And so once you prove that, you have proven one of these two bullets in that are needed to prove Howe duality. And of course, now you need the second one. But in this case, you cannot use anymore this idea, because G prime is now a bigger group. However, you do what you do, you're using now theta lifting to prove that there are many, sufficiently many representations, this times pi prime lambda prime. This is non-zero. So in other words, what you do, maybe we'll just call this lambda the same. In some sense, think of this pi lambda prime, the lift of pi lambda. In fact, you don't really need to work with the whole minimal representation, just with this subspace G prime generated by V0. And then, so when you act by G prime on V0, you know, for all those lifts, you're going to have this space non-zero, and then you have to prove similar, you know, lemma relating more or less. So I'm cheating here because we don't get everything in the lift anymore, to prove this other identity needed to prove Howe duality. So this is this other identity. See, I forgot now if I mentioned this earlier in the talk, but you know, this identity, and also you know, this one over here, they're kind of very similar in flavor to, you know, Jorge's talk yesterday. I just would like to remark that. Well, I guess that's it. I mean, so I'm sorry if I'm gone a little bit short on time, but basically just summarizing quickly, or maybe I can just go briefly over the ideas since I have time. So the first, first thing what I try to describe is this Tits construction, where you get this class of dual pairs, and maybe I didn't really emphasize that in our situation, this these groups can be F4, E6, E7, and E8, and so these dual pairs are, G2 times this group, and this group can be, it's either SO3, and in this case, you see, in this automorphism of H, in this case, it's disconnected because E8 has outer automorphism, and so the corresponding group is PGL3, semi-direct product Z mod 2. This is Jordan algebra. In this case, the split form of Jordan algebra is the matrix algebra, 3 by 3 matrices. And of course, PGL3 acts by conjugation, but then you have a transpose also. Transpose is automorphism of Jordan algebra. In Jordan algebra is just AB plus BA commutative. You make multiplication commutative. And so you get disconnected group. And you see, if you don't work with disconnected group, you're not going to get Howe duality. And then you get PGSP6 in E7, and of course F4 in E8. So these are really the dual pairs. And so I have really later concentrated on these 3 cases, sitting in E7, E6, and E7, and E8. And again, here I explain, what is the desiderata, basically to have a dual pair correspondence. You can always define this theta V for any V reducible. Just you look all the forms from pi to V, take the quotient by intersection, you get this factorization. And to prove duality, you have to have duality, you have to have this theta V is a finite line that has unique irreducible quotient, and also for the lifts on the other group. And then for spherical, you want to, yes, now I know what I wanted to make a comment. For spherical, we can prove the Howe duality conjecture if we prove these identities. So what Howe does in general, and here I have shown you how to do this with some sort of trickery. It's really non-trivial trickery, I think. So what Howe does, this is a good way to finish. So, because maybe somebody will ask this question, so this way I'm answering, I have some time. So what Howe does is, here is this K sitting here, and K prime sitting here. And then he looks the centralizers of K inside the ambient group and gets M prime and M. And then first thing that one needs to study is these dual pairs, Km prime and Mk prime. These are the actually dual pairs where one of member is compact. And the group M and M prime are Hermitian type. And what you're getting highest weight modules when you're lifting from K and K prime. And then there is a, so these highest weight modules are, of course, generated by highest weight types and so on, which are basically K prime and K types, roughly speaking. And then you have this notion of joint harmonics for which you have a dual pair correspondence. And these spaces of joint harmonics are used to, build these identities that in exceptional case, I simply use the space of K fix, L fix vector for this large group. So unfortunately, what happens in these exceptional dual pairs, so when G is G2 and G prime is, let's say, automorphism for Jordan algebra, then you don't get any bigger groups. In other words, when you take centralizer of K, you get G prime, and when you centralize of K prime, you get G. And my G and G prime are basically, except in one case, PGSP6, are not even Hermitian symmetric type. So I do have actual ideas how to define those harmonic matching types, but this doesn't help me to make proofs, unfortunately. In Howe case, also the fact that you can compute these lifts, make proofs of those identities almost banal compared to what I had to do in even the spherical case. All right, so with this note, I'm going to finish. I knew I wanted to say something now. Luckily, I went over everything and I recalled, but now I'm definitely finished. Thank you.